Okay, so today I want to talk about the third postulate of quantum mechanics. Again, I'm taking this kind of slow because I want to be able to really understand the basic foundations of quantum mechanics. If you guys don't know this yet, eventually I'm going to get into some of the more complex, interesting stuff. So hang tight, and we're gonna keep on going through the postulates here. So this is postulate number 3. Any measurement of the observable associated with an operator A, for any measurement, I think, yeah. So for any measurement of the observable associated with operator A, the only values that will ever be observed are the eigenvalues little a, which satisfy this eigenvalue equation. All right, so we kind of touched upon this a little bit in the last video, or this concept of operators. So I'm going to say 4. I'm actually going to make this a little bit nicer here. So this is for any measurement. Okay. So I think it would be most productive to consider this equation right here. So e to the I p x plus e t, where p is a momentum and x is a position. Okay. And we actually want to do I over h bar. Here, I'm going to do I over. And I'm starting off with this because this is a function that can easily, we can easily see how this function could be put into an equation that looks like this. If this was psi, right? The derivative, like we can offer the derivative of e to the anything is gonna have that same e to the anything in there, just with something out in front. And this already takes that form here. So this is a very good candidate for satisfying this relationship, right? And we know from Euler's formula, that this is equal to the cosine of px et. Notepad is bugging out again. Just quick. And plus I sine of same thing here, px plus et, like this. So this is the most generalized wave we could talk about. This is a wave with the complex components and real components. The real components are right here, and the complex part is right here. So this is real, and this is complex. So, and this is sort of the total wave. Okay. And it can all be meshed into this e, this exponential right here. So this here is a wave, right? This here is a wave. And what's interesting, I remember so when I studied this a little bit deeper, this I right here is really important. Because if this I wasn't here, then this wouldn't be a wave, right? This would just be an exponential. So I has this ability of taking an exponential to a sinusoid. Okay. And we could see now, if we were to operate on this with some operator, like some derivative operator. Take, for example, if I were to take the derivative of this, so if I were to take say, for example, if I were to take I h bar d dt of psi, well, this is going to equal, so I'm taking the derivative of this with respect to time, right? So this is going to be, let's see here. This is going to be IH bar, and then we're going to bring all this down here. This is going to be I E. I'm going to actually put a negative right here, because then we'll see why. IE over H bar times our exponential back. Negative I H bar on, I'll erase this guy right here. By putting a negative here, we're just changing this sign right here because we know that the sign is anti-symmetric. So by putting a negative out here, we have to put a negative right here. But that doesn't really change anything. We have P x plus ET like this. Well, so this here's psi, right? So, and then this guy here is going to cancel. So this guy here is going to cancel. And we brought that negative out. We brought that negative out here. So I times I is -1. -1 times negative can be positive. So this is equal to E psi. Okay, so what we have is this operator right here. I'll rewrite it. IH bar dt is equivalent to just multiplying our function, our wave function, by E. So, and this is what we do. This is what's called in quantum mechanics as promoting observables to operators. Okay, and we could do the same exact thing for let's see, this is going to be spatial operators. So with respect to space, IH bar like this is going to be on, this is actually what this is going to do. We can see here how this operator sort of siphoned out the energy component, or the energy component that describes our wave. This operator here is going to siphon out our momentum, right? So this is going to be the same thing as momentum. So momentum times psi, like this. Okay. And this actually has to be negative of this guy right here. This operator right here. So we could see here, so the way I sort of like to think about this is to think about this as if it was like let's see, we know from GR, or not even GR, from special relativity, that there's these things called 4 vectors. And the 4 vectors are these objects from, like, the momentum 4 vector are these objects that have 4 components to them. So we have P x, P y, and P z. Right, we're essentially just promoting these components to operators here. We're doing I H bar d dt, and then negative I h bar. These have to be negative if we're doing special relativity. Or, yeah, if we're applying this to some sort of Minkowski metric or something like that. And then this just I h bar d dy dz. These guys are negative. So these are the operators now. Instead of these quantities, here's these operators. So we go from quantities to operators like this. Okay. So this is that quantization process. This is in quantum field theory, we call this process the quantization of quantities into operators. So some people will call it first quantization or second quantization. I just like to think of it like this. I don't really like to put names on it because then you have to remember all the names, which is why I don't do very well with anatomy and stuff like that. But with that aside, this is so we can actually come back up here to this postulate. So for any measurement of an observable associated with operator A, so say this was our operator A, or this one right here. Operators usually have this little caret on top of them. If this is our operator A, then the only values that will ever be observed are the eigenvalues A, little a. So this is our little a. This again here, this is our big A. This is our little a. Which can satisfy the eigenvalue equation. So we have operator side and we have eigenvalue side. And this really works well with this function right here, right? Because this just gets, we're kind of just doing this operation right here when we take derivatives. Okay. So we could do, there's one more thing actually I want to cover before I end this, because this is really important, which is the idea of phase shifting, right? So this is our wave. Okay, so a particle can have momentum and it can have energy. And so if a particle can have momentum and energy, then it can be fully described by a wave that looks like this. All right, so I'll just rewrite this down here. So when I'm looking at this and I'm writing it down, I'm telling myself, this is a particle. This is a particle right here. A particle with two properties to it. It's traveling at some certain momentum, and it has some energy to it. So this right here is a particle. And I want to do something to that particle. Okay, and by virtue of doing something to that particle, I extract one of these two components that I'm measuring. Right? So when I do something to this particle, I am measuring either the momentum or the energy. So you could again think of this as the operator is reaching into this bin of numbers that describes the particle. Okay. And so we could sort of think of this in our last video that I posted, where an operator sort of reaches into this bin of an infinite vector Hilbert space thing, where we have our vector space, we have our Lagrangian, we have our Hamiltonian, and then we have these operators right here. I said that we have discrete operators, continuous operators. These guys are reaching in to this bin, and we're extracting some observables out. Again, we're reaching in here, and we're extracting some observables out. right? So this process, this is we can kind of think of of operators as doing this. That a particle can be represented in with a point on which, or with a momentum, a particle can be described as having a specific momentum and having a specific energy. And if we want to know what those two, momentum and energy, are at some instant in time and at some location in space, we apply this operator to it. So when we read this kind of thing, this sort of reads as, I have a particle and I want to know something about that particle. So I'm gonna apply this operator to it. Okay. And this is why this postulate 3 is sort of given as a postulate, and you don't really go that deep into it. It's because this observable here, or it's because we're assuming that we're just starting off with this exponential, and this exponential has these two properties here, and then we go from there. But we don't really understand, or oftentimes students get somewhat confused about this. It's like, why exactly are observables associated with operators? Well, this is why. It's because we can pack in all of this information into a wave. Right? And this is also very good. This is a wave, and we've said in the past that particles can act like waves due to the double slit experiment. Right? So this packs a lot of information. But furthermore, we also want to entertain this idea of a phase shift. Okay, so I think I mentioned this briefly, but a phase shift. So suppose we have this particle here. I'll just erase some of this. So this is a particle, okay, and it has some property to it, and it has two sort of properties to it: a momentum and energy. But nothing's stopping us. Again, nothing's stopping us from putting a number right here. We'll call this a number. Okay. This is what's called the phase of the particle. So this is a phase. And we can sort of think of this as, okay, well, if we put a phase right in here, we're going to put a phase right in here. And we're going to put a phase right in here. And so by virtue of doing that, this is you go back all the way back to your algebra class. For any function, and if you put this phase inside the function, it just shifts the function over. It doesn't do anything to fundamentally change the overall shape of the wave. It just kind of shifts it around. So you could suppose we had a graph that looks like this is our original wave. This is our original wave, and our shifted wave might be something like that. So this is with the phase shift, and the red is without the phase shift. And again, this is a perfectly fine wave. It's just shifted, right? It's still a solution for the differential equations that we'll come by, because nothing changes about the overall structure of the wave. So, and we'll see this when it comes to advanced quantum, where we'll add this other e to this e to the I h bar phi to our particle. Let's see here. This I h bar. I'll just write this over again. Like this. And we know by the nature of exponentials, this is just this right here. So this is equal to that. So, and also before, I want to cover a lot of this here, but before we can have, this could be positive or it could be negative. When it's positive, when this is positive, we have to choose our operators dually, but this is ultimately going to tell us, okay, there are particles that have this wave-like structure to it, right? And these elements within the wave describe the particle. This right here, this describes a phase shift in the wave. So phase shift. And this right here is going to tell us, okay, when we perform an operator, we are going to get some particles, depending on what this guy is, we're going to get some particles that have negative energy and positive energy. So for example, if this was negative, right, if this was negative, ultimately, this is going to be negative, right? But ultimately, this is going to be negative, and so when we extract this guy out with our operator, we're going to get negative energy. And we have to be careful. So we have to be careful with this plus and minus stuff, because we're going to see different forms everywhere in different books, right? But if we want to, if it's most of the time, excuse me. So most of the time, what you're going to see here is actually a difference. This is what's in this argument is a difference right here. So this is a difference, which is going to enable us to say, well, okay, this here is how we're going to define our operator, and this here is how we're going to define our operator with this negative here and a positive right here. Okay. But again, nothing should be stopping us from changing this to plus or minus or anything like that. What's essential to know is that the operators are going to reach into this exponential and they're going to extract something out. They're either going to extract the momentum or the energy, or you could find some operator that just extracts the phase, but the phase, if you wanted to do that, that's a little bit more complicated, because the phase, and then this is a big part of quantum mechanics, but the phase could be a function of x, or a function of t, or a function of both. And if it's a function of both, that complicates things a little bit, right? That complicates things a lot, actually, because if it's a function of both, then we really have to pick our operators. Yeah, I lost the word there. Operators, to be able to get this form right here back. Right? But in simple speak, if this was just a number, then we can just do this. And when we do this, this right here, if nothing changes about the particle, about the nature of the particle, when we do this, we can make some measurement or something like that. But when we do this, this is associated with something called a gauge. Okay, now my pen's bugging out. U-G-E. Gauge. Transformation. Okay, my pen's bugging out, so I'll quit soon. Or I'll stop this video soon. But yeah, so I think we have beaten up this postulate enough, and I think we can understand exactly why this postulate is the way it is. We start off with an exponential that can represent sine waves and cosine waves, and then we go from there. So with that being said, I don't want to keep this on going for too long, so I will see you guys in the next one.